The term tide is a little misleading because most people associate it with the moon's orbit around Earth, which causes the ocean's ebb and flow at the shore. However, astronomers believe that the water is washed in and out by a force, more precisely, a shift in a force. The near side of the moon has a greater gravitational pull from Earth than the far side. The moon physically bulges out into an oval, or, more precisely, an ellipsoidal shape as a result of this stretching effect. The tidal force is the name given by astronomers to this variation in the force of gravity. Earth bulges as a result of the moon's gravitational pull. This indicates that Earth has two tidal bulges, one on its side facing the moon and another on its other side.
Meanwhile, the Earth turns once a day. The moon's gravity pulls an area of our planet farther away from the center of Earth when it goes through a tidal bulge. These changes in water flow cause the ocean's height to rise on the bulge, a phenomenon known as high tide. We receive nearly 2 high tides per day since this occurs on both bulges, moving toward and away from the moon. The tides also have another effect. The rotation of the Earth, the moon, and their orbital motion all include energy that is locked up. The rotational energy of the moon had to go someplace as its spin grew slower over time. A portion of that energy was released into the moon's orbit, while the remainder was converted to friction in the moon's interior. An orbiting object moves away from its primary host and onto a higher orbit when you inject energy into it. This indicates that throughout ages, the moon has migrated farther away from Earth after beginning life much nearby. Our satellite is still regressing from us at the glacial pace of about 4 millimeters per year since our planet's rotational energy is also being fed into the moon's orbit as it slows down Earth. Tides, the rhythmic rise and fall of sea levels driven by gravitational forces, play a crucial role in shaping the Earth's oceans, landscapes, and atmosphere. Beyond Earth, tides extend their influence throughout the solar system, affecting celestial bodies in diverse ways. This detailed exploration elucidates the mechanisms behind tides, their impacts on Earth, and their broader implications for celestial bodies within our cosmic neighborhood. The primary driver of tides is the gravitational pull between Earth and the Moon. As the Moon orbits Earth, its gravity exerts a stronger pull on the side of Earth facing it, causing the water to bulge outwards. The same gravitational force creates a bulge on the opposite side of Earth too. This happens because the Earth itself is being slightly stretched by the Moon's pull. The Earth spins on its axis, and as different parts of the planet rotate through these bulges, we experience high tides. Sun's contribution, a balancing act, while the Moon is the dominant player, the Sun's gravity also influences tides. Though weaker due to its larger distance, the Sun can either amplify or dampen the Moon's pull depending on its alignment with Earth and Moon. When the Sun and Moon are lined up, during new moon and full moon, their gravitational forces act together, creating higher high tides and lower low tides, known as spring tides. Conversely, when the Sun and Moon are at right angles to each other, during first and third quarter moon phases, their pulls partially cancel out, resulting in less dramatic tides called neap tides. The relentless rise and fall of tides play a crucial role in shaping Earth's coastlines. The scarring action of tides erodes rocks and cliffs, while the constant movement of water deposits sediments, forming beaches and barrier islands. Tidal flats and estuaries, teeming with life, are nurtured by the regular inundation and exposure brought on by tides. These areas serve as vital feeding grounds and nurseries for a variety of marine creatures. Tidal influence beyond Earth. The Sun-Moon gravitational interplay doesn't stop at Earth. Tides, though less noticeable, occur on other celestial bodies with large moons. For instance, Jupiter's moon Io experiences the strongest tidal forces in the solar system due to its proximity to the giant planet. These immense tidal forces are believed to be responsible for volcanic activity. Lunar tides. Beyond Earth, the moon's gravitational influence generates tides on other celestial bodies, such as Io, one of Jupiter's moons, where tidal forces from Jupiter cause intense volcanic activity. Saturn's rings. Tidal forces play a crucial role in shaping the intricate structures of Saturn's rings, causing gravitational interactions that create gaps, waves, and shepherd moons. Exoplanetary systems. Tides can also impact the habitability of exoplanets by influencing their climate, ocean dynamics, and geological activity, shaping the potential for life beyond our solar system. The moon's slow retreat. Tidal forces have a more subtle but long-term effect on Earth's rotation. As the moon pulls on the Earth's bulge, it transfers some of its angular momentum to Earth's rotation. This ever-so-slight transfer is gradually slowing down Earth's rotation, making our days longer by milliseconds per century. Conversely, the moon is also pushed slightly farther away from Earth due to this energy exchange. Future studies and applications. Climate modeling. Understanding the complex interactions between tides, ocean circulation, and climate is essential for accurate climate modeling and predicting future climate change impacts. Planetary exploration. Studying tidal effects on other celestial bodies provides valuable insights into their geological processes, internal structures, and potential habitability, guiding future space exploration missions. In conclusion, tides are more than just a rhythmic curiosity of our oceans. They are a testament to the gravitational dance between celestial bodies, shaping our planet's coastlines, ecosystems, and even the length of our days. The influence of tides extends beyond Earth, hinting at their role in the wider dynamics of our solar system.